This is tutorial 4 and it's question number 2. In this question we have a Pelton wheel and 4 nozzles. They're connected to a parallel pipeline system with equally sized pipes of diameter 0.406 meters, and the length of the pipes is 4,000 meters. The coefficient of friction, F, friction factor for the pipes 0.032. Pelton wheel is 330 meters vertically below the supply reservoir. Total power of all 4 jets equals 1.5 megawatts. Calculate for maximum efficiency of transmission conditions. 2.1. The total mass flow of fresh water at 12 degrees C required and the jet diameter. Alright, so I have written the information down. 4 nozzles, pipe diameter, the length, friction factor, total head, 730 meters, power of the jets, and also looked up density of water at 12 degrees C is 999.58 kilograms per cubic meter. So we know that for maximum conditions, HP is 2/3 of H total, because we have 1/3 for maximum conditions, 1/3 lost due to friction in the pipelines. We also know HF is equal to 1/3 of H total. So power at the jets mass flow rate times gravity times HP. Alright. We also know that power equals rho GQH and mass flow rate is rho Q. And that's how we come out with that formula. So making our mass flow rate the subject of the formula, we get power divided by G HP. And if we substitute, we get 1500 times 10 to the 3 is the total power available at the jets. We divide that by 9.81 and 2/3 of 330 meters, which is the total head. So our mass flow rate would be equal to 695 kilograms per second. Now, we also know that the HP, which is the power available, is 2/3 of the total power in terms of head. So that's 330 times 2/3, it'll give us 220 meters, which is the power head available at the jet. Alright, so HP is equal to V squared over 2G, and that is for the jet. Therefore, velocity of the jet is equal to the square root of HP times 2G. Now we have to divide that by 4 because there are 4 jets. So velocity of the jet. Substituting, we get the square root of 220 times 2 times 9,81, and we divide all of that by 4. So velocity of the jet is 65,699 divided by 4, or 16,424 meters per second. Alright, we also know that Q is equal to VA, and that's also equal to our mass flow rate over rho. So therefore, we can say Q is equal to 695, the mass flow rate, divided by density of water, 999,58, and that gives us a discharge 0.695 cubic meters per second. Q is also equal to VA, and we are trying to find out the size of the nozzles. It's equal to V times pi over 4 d squared. So the diameter of the jet is then equal to the square root of Q times 4 over pi times V. Zero comma 695 is the discharge, times it by 4. Alright, just delete that. Divide that by pi. And also the velocity, which then is 16,424. And our diameter of a jet the diameter of the jet is equal to 58 millimeters. Alright, so that's the mass flow and the required jet diameter. So question 2. Is the number of pipes required for the system. So we have our dn is equal to the fourth root of dp to the 5 n squared over over 2FLN squared. So we end up with dp to the 5 n pipes squared over 2FL n jets. Right, so taking the number of pipes subject to the formula, we get the square root of d jets to the 4 times 2 FL n jet squared over dp. Right, let's substitute into that formula. 0.058 to the power of 4 times 2 times 0.032 times 4,000 and 4 squared over 1,406 to the power of 5, and number of pipes will then equal to 2,04, say 2 pipes. Alright, now we have to work out the Reynolds number of flow in the pipes with water temperature equals 12 degrees C. Alright, mu is equal to 0.001236 kilograms per meter second. We looked that up for 12 degrees C water. So substituting, I get 999.58 times 0.406, which is the velocity, times 2,684 down to the pipe, divided by 0.01236, which is mu. And the Reynolds number then equals 88.1267. Alright, so remember V is equal to 0.695 over pi over 4, 1,406 squared times 2. Velocity in the pipe is 2,684 meters per second. That's where that velocity comes from. And that's the end of question 2.